welcome to today's video. My name is Iwan Ntow Hiaw, and in this video we are going to be discussing three topics. We are going to be discussing cache memory, cache read operations, and the effects of hit ratio on average memory access time. So let's start with cache. Cache memory is a small and fast memory that's located close to the CPU. It stores data and instructions so that the CPU can access them quicker than if it had to access them from the main memory. The cache memory has three types, which is L1, L2, and L3. Let's start by explaining the L1. The L1 cache, which is the level 1 cache, is the closest and the fastest cache to the CPU core. It's typically located within the CPU core itself, and it is designed to store the most frequently used data and instructions that the CPU needs for its immediate operations. It has two areas for storing data and instructions, which means it stores data and instructions separately. It stores data on the L1D and instructions on the L1I, and the typical size for those two areas are both 16 kilobytes to around 128 kilobytes. And because of its size and its location, it is the fastest and the most easily accessible one by the CPU core. So now let's go to the level 2, which is the L2. It's normally located either within the CPU core itself or on the same package as the CPU, but outside the CPU's individual core. Its purpose is to store data and instructions that complements the data and instructions stored on the L1. So it holds data and instructions that didn't fit in the L1 cache, and it's also slower than the L1, but it's faster than the RAM, which is the main memory. So it's still quicker for the CPU to access data and instructions from the L2 rather than going to the main memory to fetch the data. The typical size for the L2 is around 128 kilobytes to around 1 megabytes or more, depending on whichever CPU core or whichever machine or computer you're using. And it is very quick for the CPU to also access data from there, but a little bit slower than the L1. Now let's go to the L3. The L3 is typically shared among multiple core or CPU core on the same processor chip. It serves as a share pool of cache data that all CPU cores can access. So it helps in situations where data needs to be shared among cores, and its size is around 2 megabytes to more than maybe 8 megabytes to around 64 megabytes. Because it's the largest, it has to store a lot of information, or which is the instructions and the data stored on it. So in a real life scenario, let's compare the CPU, or let's illustrate how the CPU works to, let's say, a supermarket. In a supermarket, when you go to the supermarket, you see there are shelves there which contain items being displayed, and you, being the shopper, will hold a basket for shopping. The basket represents the cache, and the items on the shelves are the data. So let's say the shelves itself is the main memory, which is the RAM, and you, the person shopping, is the CPU. So what you do is that when you go to the supermarket, you normally take stuff you normally use or stuff you will need in the future, and you put them in a basket so that when you need them, is easily accessible, or you can access them quicker at home, so that you don't have to go back to the supermarket to buy the stuff each time or every time you need to use them. You have to go back to the supermarket to buy them. And let's say you need something that's not parts of the stuff you bought or the stuff you place in the basket. What do? You reach back to the shelf and you take the item. So that's how the cache memory works. The cache memory stores data which will be needed in the future or the nearby future so that the CPU can access it quicker when it needs them than rather going to the main memory to fetch them. So using this illustration, we've explained how the cache memory works. Now, the cache memory can be used in various departments, which is it can be used in a gaming department also, or the gaming sector. You see, when you are playing game, let's say you are playing FIFA. You play FIFA, maybe before you play the game, the settings does not fit your style of play. So maybe you go to the controls, you change the controls to maybe alternative or classic, or maybe A, B, or you change maybe where the passes, the lobbing is, the shot is, and those stuff. When you change those stuff, you see the on the FIFA, it tells you to store it. When you store those informations, they are stored on the cache memory, so that when you are playing the game, you can access it, like the CPU can access it quicker, so that the game will not like slow down or anything. Imagine you are playing the game and the pass and the the crossing and those stuff, it changes from where you chose to like change it to another area. You see, it won't work that way. So what the CPU does is that it stores those informations. The cache memory stores those information so that the CPU can access them quickly, so that when playing the game or whenever you are playing the game, you can access those informations quicker. Let's say even you are playing not even FIFA, you are playing any other game like those Candy Crush and other stuff. Whenever you are playing the game, you see the whenever you play the game, whichever level you get to is stored in the cache memory, so that when you come, you know where you can continue from there. So the CPU will be able to access them quickly. So when you go, you just see I got to level 2 or level 3. So now I'm continuing for level 3. It stored that information. So when you just come, you just continue from there. That's how the main memory and the cache memory works. Now in the cache memory, we can also get, we know how the cache memory works in the web browser also. Whenever we make searches or we search, see, we go back, then when you tap on the search bar, you see there's some suggested searches there, which are maybe the most frequently or the most recent searches you've done. Those information or those data are also stored in the cache memory, so that you as the user can access them quickly whenever you go to the search bar and you want to do some search, and maybe you want to search on those stuff again, you can just access them. And the operation system also uses that same principle or method, which is the cache memory, to help it store data which are frequently used, to improve the performance of the operation system by reducing the number of times the CPU has to go to the main memory to fetch data. So in this illustration here, you can see, in the illustration here, we can see how the main memory and the CPU and the cache memory all work together. So the cache memory, being the intermediate, stores the data which are frequently used by the user over there. So when the CPU needs them, it just comes to the cache memory, then it takes them or retrieves them, then uses it for its operations needed. So when the data that is needed from the CPU or by the CPU cannot be accessed on the cache memory, it then goes to the main memory to fetch those data. Then it stores maybe a copy of those data on the cache memory, so that in case it needs to use that, it goes back, it comes back to the cache memory and it's quicker for it to access. Then it goes to, it takes it to its, then it uses it for its operations again. So let's say in a situation whereby the cache memory is full, but the CPU needs some data and it fetches it from the main memory, and it might need that data in the nearby future. What it does is that it will delete or replace the information from the main memory in the cache memory with the least frequently used data and instructions, so that in the nearby future, if it needs those information again, it will just go to the cache memory and use it. So that's how the cache memory works. And one thing about a cache memory is that it's volatile. That means it ceases to work when disconnected from electricity. So maybe when you off the computer, the cache memory isn't working, but when you turn it on, it works. That's how the cache memory works.
Hello, my name is Kwabena Tutu, and today I'll be explaining cache read operations. So, a cache read operation is a memory access operation in which the processor attempts to read data from the cache. If the data is found in the cache, it is called a cache hit. If the data is not found in the cache, it is called a cache miss. So, in cache read operations, what happens is that the CPU wants to process a specific data. So the first place it will look for that data from is the cache, because the cache is close to it and it's very fast. So it keeps the most frequently used data. So it will go to the cache. If it finds it in the cache, we call it a cache hit. It will take it from the cache. But if it doesn't find it in the cache, it will have to go into the main memory to go and look for it. That's what's called a cache miss. So in a cache hit, the data is read directly from the cache, which is much faster than reading it from main memory. This is because the cache is located closer to the processor and has smaller access latency. In a cache miss, the data must be read from main memory and then copied into the cache. This is slower than a cache hit, but it is still faster than reading the data from a main memory directly. So if in the cache hit, the data, if the CPU reads from the cache and it doesn't get the data it wants from the cache, that being a cache miss, it will go into the main memory, and when it finds the data it wants in the main memory, it will copy it into the cache before it will come and copy it from the cache. Yes, even though it's longer, it's still faster than reading it from the main memory than bringing it directly to the processor. So, to the next point. The cache read operation is typically performed as follows. 1. The processor generates the address of the data to be read. 2. The cache controller checks if the data is already in the cache. 3. If the data is in the cache controller reads the data from the cache and returns it to the processor. 4. If the data is not in the cache controller reads the data from main memory and copies it into the cache. The cache controller then returns the data to the processor. So this is how the cache read operation is performed. Firstly, the processor will generate the address of the data to be read. So once the address is generated, the cache controller will first check if the data is already in the cache. If it's already in the cache, then it will copy it directly from the cache and give it to the processor. So 3, if the data is in the cache controller reads the data from the cache and returns it to the processor. That's it. So, but if 4, the data is not in the cache, then the cache controller will go and read the data from the main memory. So when it reads it from the main memory, it will then copy it into the cache. Then the cache controller will then return the data to the processor. So that's it for cache read operations, and I will let my colleague continue from here. Thank you.
My name is Prince Addo, a member of Group 8 and Group C Computer Science. I will be talking on the effect of hit ratio on average memory access time. Before I move into the video, I would love for you to subscribe to the channel, hit on the bell notification to receive notifications anytime we upload a video. Don't forget to like the video as well, and leave a comment on anything you don't understand in this video, and we'll be happy to assist you. Now, before we dive into the effect of hit ratio on average memory access time, let's talk a bit on cache hit ratio, what it is. As my colleague explained earlier on, we say it gauges how effectively a cache memory system operates, and then it tells us the percentage of memory access requests that are smoothly retrieved from the cache without the need to fetch data from the slower main memory, also known as the RAM. Now, on the effect, we'd like to touch on lower hit ratio, which is also known as the longer access time. Now, before I explain further, let's take a look at a picture I have here, diagram I have here. This is the cache hit, where a user requests something from the cache, and then the cache, because it already has stored data that the user is requesting for, returns the data that the user has requested to the user. So instead of going through to the main memory, the cache here makes the work easier, and then it shortens the time, the duration at which a request should move from the user to the cache, and then from the cache to the user. Now, on explaining on what lower hit ratio is, imagine you have a lower hit ratio. It translates to a lengthier average memory access time. Why? Well, more requests result in cache misses, forcing the system to retrieve data from the main memory, which is slower compared to the cache. Now, this here kind of serves as a negative effect. Why? It makes mention of a cache miss here. This diagram here talks about what the cache miss is. Additional requests are sent all the way to the original server, in our case, the main memory. When a user makes a request, the cache saves data, and if it has a maximum amount of data and then can't save extra, and a user requests for data, when it gets to the cache, because the cache can't save a more amount of data, it has to go to the main memory, which is the slower memory, to retrieve data from there, move it back to the cache, and then moves it back to the user. As a result of this, there are cache misses, because when there's too much data that the cache can no longer take, it gets rid of data that is not frequently requested from a user because it can't contain more. It gets rid of some of its data so it can be able to store new data in its memory. So it moves back to cache hit, where there is faster request and then returns. Now, let's create a scenario here. Let's take a closet and then an attic. We all know what a closet is. An attic, on the other hand, is a top of a building, very utmost top of a building, where people tend to use the place to store stuff of theirs that they don't use all the time, they don't need almost all the time. In our scenario here, we use the attic there, to store clothes that we buy, let's say we wear occasionally, or we think we don't really need for usage all the time. Now, when we need clothes, we need a clothes to go on an occasion, and we search for our closet and we can't find the clothes we want. We have clothes there, and then it's not let's say, suitable for the occasion we're going to, and we know we have a cloth, we have a cloth that we can wear, which is in the attic. And that means we need to climb staircase to go to the attic and then retrieve or take the clothes that we need there. That, as a result, takes a lot of time, because you now have to go to the top, take the cloth, climb, move down. It takes a lot of time. That is where the cash miss here talks about. So let's say you have a lot of dresses in your, we're using the cash miss here to explain this, where you have a lot of dresses in your closet. It becomes too much that there's no room for new ones. When you get new clothes, you'd want to move, because you know the old clothes are not, they're not spoiled. You'd want to move the old clothes from here to your attic for later use, so you can store the new clothes. Same as the cashmere here I explained earlier on, where this is your cache, and then because the request coming in from the user, it's more, and then the data that the user is requesting is not in the cache. Because the cache is full, it needs to get rid of old data that is not frequently requested for anymore, so it can be able to take in new data. Now, so we use the closets to explain this, where if you often can't find the clothes that you need to go in your closets. You have to go up to the attic to get them, and it takes more time. That is what I explained using the longer access time. And then I also use the cache miss, where you need to get rid of some of the clothes here, move them into your attic so that there can be space for new clothing here. Okay, going on the second effect on hit ratio on average memory access time, we have increased cache utilization, where high hit ratio we say is a golden ticket, because it suggests that the cache is a champion at storing frequently used data, and this leads to more cache hits and optimized utilization of cache resources. Now, let's explain this too. Imagine you have a small shelf for your favorite books, where this is our shelf, and then this is a library. We're using this to explain. Now, the effect here says that the cache stores frequently used data, and then this really helps because it helps in optimizing utilization of resources that are in the cache. Now, when you have a bookshelf in a library, you store your frequently used books. Let's say you have a lot of books in the library, and then the most used ones that you have, you use all the time, is your computer architecture books, your C++, notes, and then your logic, and then let's say physics. You have it in the main library. It is very easy to get a book that you frequently use. Let's say you use a computer architecture book frequently. Let's say on every Wednesday or every Tuesday, every Monday, you make sure you go through your lecture notes, you go through your books on computer architecture, so you're always updated on, you're always more informed before class begins on every Wednesday. It makes your work much easier, because you wouldn't have to, just like I said, physics is in the library. If I need a physics book and I can't find it in my shelf, then that means I have to go through all of these books to be able to find the physics book that I want. And so the cache plays a key role when it comes to something like this, because it stores the data that you use frequently, so that whenever you need it, it wouldn't have to take so much time for you to get the data that you want, because it is available for you whenever you need it. And it's really helpful it really comes in handy. So you can easily grab any book you want without searching the entire room. That's where the high hit ratio means. It means that the cache is storing frequently used data, making the computer faster because it finds what it needs quickly. So you have a very good memory in your computer, and you're working on a video, you're editing a video in Final Cut Pro, and then you're editing a picture or an artwork, Adobe Illustrator. When you move into your Adobe Illustrator, you continue from where you ended, because the resources that you need to work with is available in the cache. So immediately you go there, you can easily work very fast. But then, let's say you don't have a very good memory, then when you go there, it needs to reload, and it needs to pick every resource that you need from the main memory again, and it takes time before you can be able to continue with what you are doing, and that is much slower. Thanks so much. I would like to end here, and then my group member would also continue from where I ended. Once again, I urge you to subscribe to the channel, click on the bell notification so you're always posted on anytime we upload a new video. Click on the thumbs up button and leave a comment if you don't understand anything, and we'll be very happy to assist you. Don't forget, a sub to the channel is great caching. Thanks so much.
Hello guys, this is Bismark, and we are still talking on the effect of heat ratio on the average memory access time in computer architecture. Take notes. Discussing how the heat ratio of caching memory can affect the speed at which the computer processes information. Without wasting much time, please let's delve into the relationship between a heat ratio and the average memory access time. Okay, when we simply talk about heat ratio, it means the number of times the CPU finds data in the cache, that is a cache hit, and that was explained by saying a cache hit is when a cache or a data is being found in the cache memory. Okay. The heat ratio signifies the proportion of cache hits playing a pivotal role in system performance. This simply means that heat ratio, it does a major or an important role in the performance of your computer. So just that if you want your computer to perform faster and quick as possible, you just avoid a cache miss. For example, if a requested file is found in the cache memory 5 times out of 10, then the heat ratio would be 50% or 0.5, and the heat ratio can then be calculated by the number of hits, that is the number of cache hits divided by the total accesses, where the total accesses is the cache hits plus the cache misses. Heat ratio is a measure of how effective the cache is in storing most frequently used data, as explained previously. Okay, this number is an important part of how a computer processes information, as it will have an effect on the time it will take to access resources. Let's talk about the AMAT, simply meaning the average memory access time. And this is the weighted average of the time it takes to access data from different levels of memory, which was already talked about, that we have the L1, the L2, and the L3 memory with their different sizes of memory storage or spaces. And this AMAT is considered with both the cache hits and the cache misses. And when we go on to say the average memory access time can be calculated by the hit time plus the miss rate times the miss penalty. And when you talk about the hit time, it means the time it takes for a cache to be found in a cache memory or a file or a document or something to be found in a cache memory. And when it comes to miss rates, then the miss rate has to deal with the rate at which a cache is missed. And going back to miss penalty simply talks about the time delay in missing a cache. Cache hits have lower access latency, which leads to quicker processes by the CPU. Okay, let's move on to the main point. As it states, the effect of hit ratio on the average memory access time. The hit ratio directly affects the average memory time, which is how long on average it takes to access data. The higher the hit ratio, the faster or lower the amount, and vice versa. So when the hit ratio is high, it makes the access time very low or faster as in a quick possible time. And the amount, which is the average memory access time, involves two components, and I've already made mention of that, which is the time it takes for a cache hit and the time it takes for a cache miss. Let's continue. Describing this diagram here. Okay, let's take this to be the CPU and this to be the cache or the cache memory, and this being our main memory, which is the slower main memory, which we normally call the RAM. Okay, so when the CPU wants to work on a file or something, it has to come to the cache memory to pick up the file, go back and process it. But in a case where it comes successfully and finds the file here, going back within the shortest possible time, working on it, processing the file or data, it's called cache hit. And taking the scenario where the CPU comes here without finding the data it wants to work on, it has to come out and go back to the main memory for it to be allocated, come and place it here and take it back to the CPU before it can be processed. And describing that process from the main memory to the CPU the main memory to the cache memory to the CPU, it's very tedious, as you can all imagine, because the time it will take the CPU to allocate file here is different from the time it will take to allocate file in the main memory. And by doing that, it delays the time, which causes the low performance of the computer. And when it happens that it finds the files here and processes it, it improves the performance of the computer. I hope that is understood. Okay, let's move on. Illustrating the hit ratio effect with the graph. Okay, so we'll put the hit ratio on the vertical axis and the access time on the horizontal axis. So with the increase of hit ratio, automatically the access time also increases, which was made mention in the previous slides, that the increase in hit ratio also increase the time, it decreases the time it takes for the time it takes for a file to be accessed. So increase in hit ratio also has Okay, as the heat ratio increases, the amount decreases, which was explained that the time it takes for a cache to be located will be lower and much faster. So let's say the heat ratio increases by 5, then it means the amount or the access time will be much shorter. And this means that the graph will be projected high, or let me say it will have an increase in heat ratio. All we are saying here simply means that the more often we find data in the cache or the high heat ratio, then it means the quicker our overall memory accesses become. Okay, let's move on. Putting all we have talked about here in a real world scenarios, imagine you playing an immersive video game like GTA, FIFA 23 or something. A high heat ratio, that's the CPU, ensures that the game textiles, models, and the resources are readily available in the cache, as explained in the diagram in the picture previously, facilitating quicker access time. All this I just read here simply means that for the CPU to ensure the game moves smoothly and, let me say, a normal performance, then it means the models, the textiles, and the resources must be readily be available in the cache, so that when the CPU gets hold of it, it quickly processes it for the user to encounter or enjoy a smoother game or free run of the game. And a low heat ratio might result in the loading or delays of data that needs to be fetched from the main memory. Okay, let me summarize all I've said. It is important to maintain a high heat ratio in order to keep amounts low, as this will have a positive effect on the overall performance of the computer. And before I started speaking, I mentioned that when you want your computer to be faster or quicker, you just have to avoid cache misses, improve in the cache heat, that's the heat ratio. And when you have a high heat ratios, the performance of the computer simply is superb. Okay, understanding the heat ratio's effect on AMAT helps us optimize performance and design more efficient systems. Thank you. And thank you for watching this video. I'll see you next time. I hope you like, comment, and subscribe to this channel. Goodbye. Bye bye.